So I wanted to sign on and talk about filters. So it's a really big topic, and I might take a couple of different shots at this. The reason filters is such a big topic in digital audio is basically everything that you're working with is a filter in some way. A filter is just something that processes audio, like multiplying a signal by some gain and just scaling it. That's a filter. Applying dynamic range compression, like a compressor plugin, a saturation plugin. Both of those are filters. EQ, that's a filter. Reverb, also a filter. This is like a way of mathematically describing what we're doing to signals, and there's a set of theory that gives us some analytical tools so that when we're presented with some algorithm, some equation that operates on a signal, we can sort of figure out what it's going to do to that signal. And we can tweak its design or design a different equation to operate on the signal in the way that we want to. I'll say that my favorite book for learning about this is free. You can find it online. So it is Introduction to Digital Filters with Audio Applications by Julia Smith. This is the website. If you want to learn about the math of why filters work, how to design them, this is a great place to start. It's got problems in the back. You can just sort of take a whole course in filters. Yeah, and so I want to start though not here. I mean, I think we'll cover some of this stuff, but I want to start by building something together. So let's kick open an editor. I'm gonna go to my live stream folder. Okay, I'm gonna open up two of these. I'm running on not as much sleep as I would like, so we're gonna keep the notes very handy so that I don't get confused, which I may get confused anyway. I'm cheating a little bit here. This is where we're going. Ignore this. We're gonna take every step together. Let's make a new directory. I call this stream 3 filters. All right. Cool. So we'll do the sort of stuff that we've been doing every stream. Let's make a little harness that we can use to hear this thing. All right. That's all the boilerplate out of the way. So, Julia Smith kicks off his book on digital filters with what he calls the simplest low-pass filter. And I agree. I think it's the simplest low-pass filter. And I also agree that it's a very good place to start. So we're going to start there. We're going to build it. All right. We're going to make a struct called simplest low-pass filter. And this thing has exactly one piece of state. It's a floating point number, and it's going to be the previous sample. Okay. And then here's how we implement this filter. It's really easy. It takes in the current sample, and then we're going to say float yn. I'll pause here. So in filters, y is the variable that's typically used to describe the output of the filter, and x is typically used to describe the input. So I'm just going to stick with that convention because it's what you're going to find if you go Google this stuff later. Okay, here's the filter. The output sample is equal to the current sample plus the previous sample. And then we'll just set the previous sample equal to the current sample at the end before we're done. And voila. That's the filter. That's it. It's the simplest low-pass filter. in order to listen to this, we need something to put into it, right? So there's a couple of ways that we can do this. We might want to send like a sine wave that sweeps from low to high, and we might want to just send some white noise into it. Let's do both of those things. The sine oscillator we've built together twice now, and we built the ramp last week. So I'm just going to take these, and this should look familiar. Here's just a ramp. This is like half of the envelope that we built together last week, and it works on the same principle the oscillator does. We have some attack, we have a level. Every frame we increase the level by attack samples. So, and I'm defaulting the attack to 4 seconds of audio. So we don't need to implement any kind of control structure around this because it's already exactly the ramp we want. It's going to go from 0 to 1 over 4 seconds. Okay, so we're going to have our sine oscillator. We're going to have our ramp. Okay, good deal. And then we're just going to say for int I equals 0. I is less than num samples. Plus I. We're going to say osc set frequency. So let's just sweep this from, I don't know, 20 to 20. We'll go from 20 hertz to 20 kHz. Make these floating point numbers. I'm just setting up the range here. Ramp.next. All right, so this is just going to sweep the frequency using this ramp from 20 hertz to 20 kilohertz. And then we're going to say buffer of I is equal to osc.next. Our filter. Let's put our filter in between. I don't know. Let's actually listen to this first. That way we know. That way our ears know what's happening, right? I'm going to make this quiet because it's going to go really, really high. And I don't want it to be annoying. Okay, so the program that we have right now is just going to sweep from 20 hertz to 20 kilohertz, and it's going to be a sine wave. Good luck, everybody. Clang, ++, main, our output program, filter. Okay, compiled it. And we're going to send it through aplay. 1 channel. Format is a floating point number. Sample rate is 48 kilohertz. Okay, that was still a little louder than I would like. And this isn't going to be a great way to hear the filter, but I'm doing this for a reason. Just bear with me. All right, and the reason it's not a great way to evaluate the filter, like with your ears, is because your ears don't perceive every frequency at the same volume, right? There's already going to be certain frequencies that are louder, typically the ones that are around other people's voices. Our brains and ears are sort of evolved to hear human voices, which is kind of interesting. But that is another topic. So we're going to make this filter. Here's our simplest low pass filter. Call it filter. We'll say filter.next. Could you hear the difference? I couldn't. It sounded exactly the same to me. And there's a reason for that. And we'll get into it. I want to show one other way that you can use to sort of auditorily evaluate a filter. You can send white noise into it. Okay, and we haven't done this on the stream yet. So instead of copy pasting this, I'm going to actually write the noise function from scratch. this is not the only nor the best way to write a noise function. It is certainly not the most performant way to write a noise function, but it'll do for right now. So we're just going to use the built-in rand function, which returns a number between 0 and rand max. So in order to get a number between 0 and 1, we're going to divide by rand max, make sure that's a floating point number. And then we want to put this in the range of other audio signals. So we're going to multiply by 2 and subtract 1. And that'll make it go from -1 to 1. All right, we have a white noise machine. So every frame, we're just going to get another sample of noise and send it through the filter. Like, plenty of high frequency content there. We take the filter away. It sounds a bit quieter, maybe, but that's about it. Okay, so what's going on here? Why are we building such a crappy filter? So the reason that we're building this, okay. So here is what's called the difference equation for the filter that we just built. Y of n is equal to x of n plus x of n minus 1, where n denotes the number of the sample, right? So x of n represents the current sample, x of n minus 1 represents the previous sample. This is the filter that we built. So in order to figure out what this thing does, one of the things that we might want to do is find the filter's frequency response. There are a couple of different ways to do this. This is not the easiest or fastest way to do it, but it's maybe the most intuitive. So we will plug in a oscillating function into this. We could plug in sine of omega nt, right? A sine wave. But then we wouldn't be able to figure out what the filter is doing with phase. So instead, we want to plug in a more general function. And if I'm just going to pull up something in case you hadn't seen this function before, so that this step will make sense. I want to look up Euler's identity, and I want the Julius Smith page on it. Okay, there is an intimate relationship between e to the I something and cosine something sine something, right? So e to the I theta is equal to cosine theta plus I sine theta. And I'm saying I even though it says j here. You might see this. Engineers like to use j, and physics and math people like to use I. The reason for that is because engineers often have to talk about current, and the symbol for electrical current is an I. And so it makes it really confusing when they're talking about an oscillating electrical current, which means they might be using e to the I theta to describe it. Which one is current, which one is the imaginary number. So they use j instead. We'll use I. So this function, e to the I theta, represents both sine and cosine. And what's cool about that is that lets us talk about phase, because sine and cosine are 90 degrees out of phase with one another. So this is a more general way of talking about an oscillating wave. We plug that number in to our filter. We set x of n equal to e to the I omega t, where, oops, there's a little bit of context missing here, where omega is equal to 2 pi times the frequency. Omega is often called the angular frequency for that reason. So we plug in e to the I omega nt to this function. Okay, so that means that x of n is equal to e to the I omega nt, and x of n minus 1 is e to the I omega n minus 1t. We do a little bit of algebra on this, and we pull out some common terms, and we arrive at the signal that we started with times 1 plus e to the negative I omega t. Okay, so and then I just rewrote this plugging x of n back in, because I think this lets us sort of see what is happening here. The output signal is equal to the input signal times 1 plus e to the negative I omega t. So we are altering the gain of the input signal using a function that is dependent on the frequency, using a function of the frequency. Notice there's no more n in this term here, right? When we pulled it out up here, the n minus 1, we got a term with the n and a term without the n. So this is the term without the n. It's not dependent on which sample, it's just dependent on the frequency. And if we graph this function, and let's just worry about the real part right now. If we look at the graph of the real answer to this, the real part of this expression, we see a graph that goes from 2 down to 0. And it takes 2 pi, and then it comes back up to 2. So when you're looking at a frequency response like this, 2 pi is like the sampling rate, and this middle here, this is the half Nyquist rate. This is the maximum frequency that you can actually represent. So the part of the graph that we care about is just this bit that goes from 0 up to pi. So let me run a little bit of that back. We have this function here. It is the input multiplied by this decaying part of a cosine wave, essentially. This part of a cosine wave that starts, the lowest frequency is going to be loudest, and the highest frequency is going to be quietest. So this thing is called the frequency response, because it tells us how the filter adjusts the gain of a signal dependent on its frequency. And we found it by plugging in this function that represents an oscillating signal. And I think looking at the graph, it becomes clear on why this is such a crappy filter. We don't really get good gain suppression until we're already outside of the realm of human hearing, right? If if this is 48 kilohertz, this half Nyquist point is 24 kilohertz. I don't know about you, but I cannot hear that high. Even when my ears had not been ruined by concerts, and I was a younger person, I could not hear that high. So the effect of this filter is it's a low pass filter. It's just not a very good one. It is not very steep. It's what's called an FIR filter, or a finite impulse response, because it only deals with input samples. An impulse response is where we feed a filter the following signal: 1, 0, 0, 0, 0, and then the rest of them are zeros. The impulse response is what we get when we actually feed this signal to the filter. So, if we talked about the values of this over time, we would get 1 plus 0 is equal to 1. And then we would get 0 plus 1 is equal to 1. Actually, write these out. And then we would get 0 plus 0 is equal to 0. And then it's all zeros from there. So this second list that we wrote is the impulse response. It's the output of the filter when it's fed an impulse. And we can see it is very finite. It doesn't last very long. It's just 2 samples of information, and then it's all zeros. if the filter operated on the prior outputs, we don't get a finite impulse response. And that's a little bit more like the filter that we talked about last week that we made our exponential envelope out of. So here's another filter equation. The current output is equal to the current input scaled by some constant number minus the last output scaled by some other number. This filter does not have a finite impulse response. If we play the same game where we feed it a signal that's 1 for the first sample and 0 everywhere else, we never stop coming out with non-zero numbers. Y of n is equal to x of n minus 0.9 times y of n minus 1. Okay, here's a one-pole filter. We feed it this signal. Our first sample, 1 minus 0.9 times 0 is equal to 1. Okay. 0 minus 0.9 times 1 is equal to negative 0.9. 0 minus negative 0.9 times negative 0.9 is negative 0.9 squared. And then we get negative 0. You get the idea. We keep going and going and going. We never reach 0. It's asymptotic. So this is called an infinite impulse response filter, IIR. This is called a finite impulse response filter, FIR. And these have different trade-offs. Sometimes you want to use one type and sometimes you want to use the other type. The advantages of an IIR filter is it's much easier to get a steep cutoff. So I mentioned that this filter is really kind of cruddy, right? Because its cutoff frequency is the half Nyquist, and it takes a really long time to get to the point where you're getting any meaningful kind of gain reduction. So we could make a better low pass filter, and the way that we would do that is we would use more and more past sample information. So we could make a filter equation that uses x of n minus 1, x of n minus 2, x of n minus 3, 4, 5, 6, 7, 8, and so on. Uses a bunch of data from the prior input samples, and we would get a steeper cutoff frequency. The downside to that is because we had to use so much prior sample information, we're introducing a lot of delay into our processing. And at a certain point, if you want a really steep cutoff, you're going to get a noticeable amount of latency from the signal that you're sending in. With an IIR filter, we can get a much steeper cutoff a lot faster, with the trade that it is possible to make the filter unstable. We can make this filter blow up. If this weren't 0.9, but it was 1.1, the gain would actually increase every sample, and it would go up and up and up and up and up, and never come back down. So stability is an issue that you have to worry about with IIR. And sort of plus side is you also can get resonance. So if you want to have a resonant filter, you are going to want an IIR filter and not an FIR filter. And there are other trade-offs too. Like this is a topic that we could come back to and talk about. Let's build this one again. The one-pole filter deals with the prior output. So we're going to give it a piece of state that's called yn1, represent that this is yn minus 1. Initialize that to 0. It's also going to get a piece of state called a1. This is the coefficient that we scale the prior output by in our filter equation. Okay, so this is equal to x plus a1 times yn1. We return yn. And we say yn1 is equal to yn. Great. Okay, here's our one-pole filter. Let's use the one-pole filter instead of the simplest low-pass filter. All right. If we look at the frequency response of this one-pole filter, here it is. We can see that we get B naught, which is what we're scaling the input signal by, over 1 plus A1 e to the negative I omega t. And this is actually the graph of that function for various values of A. So you can see for the negative A terms here, for negative 0.9, we get a nice steep low-pass filter shape. That's this decaying exponential. And then for negative 0.8, we still get a low-pass shape, but there's like a lot less gain on it. And then for negative 0.6, it's still a low-pass, but it's pretty shallow. Yeah. So I actually realized I was surprised by the amount of gain that we were getting out of that thing, and this is actually expected. Look at the y-axis of this graph. It goes all the way up to 10. So we're getting 10x gain with this at negative 0.9. So that's sort of an issue with this filter if you wanted to use this for like, this would be a poor choice of a filter for an EQ, for example. But we can see that we're getting a much steeper cutoff than we were with the FIR filter. Like, oh, I already have that graph pulled up. Like, this way less steep than this. We can see that Julius gives us some other information here, and he puts it in this nice little box. Like, this is all you need to know about this filter. And in a lot of ways, this is all you need to know about this filter. So we get the difference equation, and this is how we would implement it in direct form, the way that we have, where we just evaluate this equation every frame. And then he gives us something that's called the Z transform. For linear time invariant filters, taking the Z transform is actually really easy. And there's a reason for that, because of something called the shift and convolution theorems. Both of those take something that's usually an infinite sum. We look up Z transform. So here's usually what is going on with the Z transform. It's usually this power series that is evaluated from negative infinity to infinity or 0 to infinity. And that's a little harder to, like, you can solve those. But for linear time invariant filters, like, you can see how closely related these are. Taking the Z transfer of something is a pretty simple operation. And you use the Z transform in order to get something called the transfer function. So for a linear time invariant filter, when you take the Z transform, you can actually take the Z transform of each of these terms individually. And due to the shift theorem, the Z transform of y to the n is just capital Y to the Z. The Z transform of x to the n is just capital X of Z. The Z transform of B1 x minus 1, we can actually pull the B1 out of it because this is a linear expression. And using the shift theorem, we can say xn minus 1 is the Z transform of that phrase is equal to capital X of Z times Z to the negative 1. And this relationship holds up with Y, and it holds up with bigger delays. If we had, x n to the minus 2 we'd end up with x of z times z to the negative 2. So the z transform of a recurrence relation or a difference equation, those are both words you're going to hear to describe this thing. In order to get the transfer function, we take the term that describes y and we put it over the term that describes z. So we separate out, we use algebra to separate out our y's from our x's. Divide x over to this side, divide this term over to that side, and there you are. You have the transfer function. You want the frequency response? Great. You plug in e to the I omega t for z, and then you have the frequency response. Those are the mechanics of like how you do stuff. It doesn't really tell you why they work. And maybe we can, if there's interest, we could cover some of that. There's a really good explanations for all this stuff in Julius's book. Yeah, so maybe next time we can talk a little bit about like, how do I know what to tune the parameters to? But I think even with the tools that we've got right here, like this lets you find a filter out in the world, like in a white paper or something, and it lets you actually implement it and listen to it. If you know how to take a difference equation and turn it into a structure the way that we did, then you can implement almost any filter that you find out in the world and listen to it. Yeah, and then it lets you, for some class of filters, you can go and analytically find the frequency and phase response and learn more about the filter that way. A lot of filters that you find out in the world aren't going to be given to you in this form. They're going to be given to you in this form. So like if you look up a paper on like how to, do this physical modeling thing or how to build this reverb, you're going to get the filter in terms of its transfer function. And then you have to do the algebra the other way to arrive at the difference equation, and then find out how to implement it from there. So this is a good thing to like practice going back and forth from these two representations, because that's going to help you get to where you can implement it. And it's also going to help you go the other way. If you have something that you've implemented, it's going to help you go and get this form of it, which lets you study it. So yeah, I would recommend Julius's book, obviously, and I would recommend like downloading some digital audio effects papers. That's a great conference. Find some filters out there and just treat them as recipes. Like don't try to understand them at first. I would say go ahead and cook a couple of them and see how they taste. Run some noise through them, run your guitar through them, see how it sounds, try to figure out how they work. Because I think that without doing that, at least for my brain, without doing that first, it's kind of hard to like understand the motivation for this stuff. Yeah. So I think we'll leave it there for today. I was a little bit scattered, and I might take another shot at this whole topic again when I have more sleep. Okay. Bye.